Hello, everyone. Welcome to this session. Today, we're going to talk about tackle persistent storage in Kubernetes. A little bit of self-introduction here. My name is Shen Yang. I'm engineering director for SUSE. I joined the Renter Labs in 2015 and joined SUSE through the Renter Labs acquisition in 2021. I'm the co-creator and product owner for Longhorn and Harvester. So let's talk about persistent storage. And well, I just want to put a conclusion there is Kubernetes persistent storage is hard. The reason is in fact get started a little bit with the history of the Kubernetes. Kubernetes initially designed to only catering to the stateless workload. So whatever storage you want to use in the Kubernetes, unless it's like just a simple temp files and you didn't want to persist, is going to go through either, say, your dedicated storage provider or your DBA, which is manage your database. Like all of this data will be living outside the Kubernetes and not managed by Kubernetes. So Kubernetes only become the consumer, and your status workload is connecting to those external providers directly to give you the access to your data. Because no workload can in fact running without your application data, almost, right? But that's pose a challenge to the cloud native applications that develop for Kubernetes. You will need to have your data for your application to make it useful, but you have to store the data outside the cluster. Of course, people will start thinking just bring them together, right? So then you will have this new concept of the PV, PVC, and the storage class introduced in the Kubernetes and try to tackle this problem. But the problem is, if you look at the market, most of storage solutions nowadays still designed with VM or bare metal central workload in mind. So oftentimes there can be a storage domain that manages the central storage appliance, which is control like how many storage they can allocate to each virtual machines or even bare metals. And that sometimes need to be manually allocated. And if you're talking about other cases, like if you're running database or other like really complicated workload in the cloud native world, and the manual advice will be, say, running those workload, in fact, outside Kubernetes and managed by your dedicated DBA team. And that is like the status quo. And their cloud providers, if you are running your Kubernetes on AWS or Azure or Google Cloud, and yes, they can provide persistent storage to your Kubernetes cluster, but if you look at the fine print, each node can only have limited numbers of volumes. I think the number for AWS is about 30, and for the other vendors is about 16 also. So that's like determines how many workload you can attach at a single node if you are using EBS volume. And because like if each workload needs a persistent storage, and you will be pretty much hitting the limit with 30 or some pod on the node. And if you are using Kubernetes on the bigger bare metal nodes, and you can, I think I saw people running 400 or 500 pods per single node, and that's why you always going to run out of the persistent volume numbers they can provide. So, and also, if you look into it more, and you will see that Kubernetes behavior in response to certain environmental issues might not be expected. For example, if a node went down, normally, if you're looking at the deployment, you expect, oh, the node is down, and my pods running on this node will be down as well. So Kubernetes will be spinning up another pod in another node to continue the workload, right? But that's not the case with the stateful set if you are not doing any modification and doing any helping to help the Kubernetes to make decision. Because Kubernetes is taking a cautious approach to the problem to avoid split brain when you have a more stateful workload running on it. So when the node goes down, your stateful workload, in fact, is not going to get restarted on another node automatically unless you or something manually to kick the Kubernetes and delete the pod running on the previous node. There will be enhancements on the Kubernetes side address those problems, but those are some of the examples. Like if you got to know Kubernetes well, and you will see that it almost looks like Kubernetes is not treating the stateful workload as first-class citizen compared to the stateless workload. I remember like a few years back, I think it's maybe in Barcelona, there's a keynote in KubeCon. Its title is Debunking the Myth Kubernetes Storage is Hard. Like ironically, I think the Kubernetes storage is still hard, and it's not a myth. It's just a different design and different concept there, and a different behavior make people like confused, and which also implied by yes, we have to address that by a dedicated keynote in KubeCon to say it's not hard. Well, so how can we help? So that's come with the topic of this session, which is Longhorn. So Longhorn is a cloud-native distributed storage system for Kubernetes, and it's built from scratch on Kubernetes and for Kubernetes. So that means like Longhorn is in fact can be deployed on like in hyperconverged way in your Kubernetes clusters to run alongside with your Kubernetes workload. And it can be run anywhere in like no matter it's data center or it's edge location, it's cloud location, like every location, as long as you can run Kubernetes, you should be able to run Longhorn. And the Longhorn is open source, as always things we do in SUSE and Apache 2 license, and also a CNCF incubating project. So in fact, Longhorn, the trademark and the project is owned by the CNCF to ensure the neutrality of the project. And SUSE is the primary sponsor for Longhorn, so we really working hard to bring Longhorn to our customer to want to see the success of this project. So Longhorn, of course, can add your persistent storage support to any Kubernetes clusters just through your one-click or just one command line, control command deployment. There are thousands of community members involved in the Longhorn right now, and more than 87,000 nodes running Longhorn worldwide right now. So you can see the latest metrics at metrics.longhorn.io. Let's talk about why. Why Longhorn was born. A few years back, I think it's around 2015, 2014, we have seen a few changes on the storage system. The first thing is we have seen that SSD and NVMe technology has become much more mature, and it makes the certain optimization for the spinning disk, which is of course related to SIG time and aggregate data stuff, unnecessary. That means so the traditional storage system, they need to really care about what the cache system will be, and they need to talk about, say, if I have data when I write it consequentially, and there is not, I want to make sure I'm not going to jump from one location to another because the SIG time on the spinning disk is very long. So those optimizations has been made obsolete by the SSD and NVMe technologies. And also, if you look at the same time, the cloud native or container technologies are booming up. And by utilizing this technology, and we can easily deploy any applications, including storage system like Longhorn to any of the destinations without really worrying much about the dependency stuff. So that also, like on top of that, Kubernetes technologies, in fact, has enabled a simple design and allow us to rely on Kubernetes to do the scheduling and availability detection. So there's a lot of, like, when I started this project, there's a lot of questions saying that how can you make sure you know what node is running what, and how do you detect the node down scenario? How do you prevent the split of brain? In fact, many of those questions has been addressed by the Kubernetes. So by building on top of Kubernetes, those questions are in fact all non-questions for Longhorn anymore. So it has been a big pain point in the design of the past storage system, but those are rendered obsolete by the Kubernetes. And those previous three items are like what we see the change in the market, like we change in the technology. But we also see the demand, which is user need an easy way to add persistent storage support to their Kubernetes clusters, because no applications runs without data, and the data is important, and we want data to be convenient, to be robust, and to be error-proven. So where is Longhorn using right now? 87,000 nodes worldwide, in fact, is everywhere. In the data center, Longhorn can be used on top of traditional storage appliance in the case that you have a dedicated storage admin and only want to allocate to the virtual machine instead of your container directly. And you can also use Longhorn on the top of the bare metal nodes, which aggregate the storage for the bare metal node and provide that to your cloud native workload on top of it. You can run Longhorn in cloud with a lot of people running Longhorn on top of EKS, and because like the limitation I mentioned before about the cloud provider storage options, and there's more reason to it. I will talk about more use case later. On the edge, when you really strive for like high efficiency, and you don't want to have like another storage appliance in your area of your edge applications, Longhorn is a really great choice on the edge as well. Longhorn can scale from one node to 3 nodes to how many nodes they have, and that is not like because Longhorn's mechanism is pretty simple on that side, and it's very scalable. In short, whenever you have Kubernetes cluster running, you can run Longhorn on top of that and provide your great persistent storage support. There will be some requirements on the Longhorn side, like hardware, how many CPUs and memory, and the network requirements. Those are big three. But if you have satisfied those requirements, you have to have like fast enough, like robust enough storage device, which means like no SD card, and that happened. Yeah, so no SD card, and as long as you satisfy those requirements, you can run Longhorn anywhere when the Kubernetes cluster runs. But how does Longhorn work? There are a few design principles we have built in the design of the Longhorn. The first thing we wanted the Longhorn to be reliable. This is storage. So Longhorn is designed to be crash consistent, and we have also multiple layers of protection against data loss, including a built-in snapshot mechanism and the backup support. So many storage vendors are really putting backup separately, but in the Longhorn, it's building concept from day one, because we know no matter how many efforts we do in cluster, if you really start say messing up, you lost your whole data center, that's not going to help you, right? So the backup, of course, you can have a third-party backup software to help you with that, but the Longhorn's backup mechanism and the disaster recovery mechanism are incremental, are highly efficient, and they should help you from day one as well. And we want Longhorn to be really has a really great user experience. So that's why I mentioned the Longhorn can be deployed just with one click, and a lot of work has been done in the background to make it possible. And the Longhorn has provided a very polished user experience, and you're not just like interacting with the console and try to learn all the commands. You have indeed a UI in front of you, which you can operate and using all the functionality Longhorn provides. We also want it to be really easy to maintain. So the first thing about that is for it to be easy to maintain, it has to be easy to understand. And I will explain more how Longhorn works in later. And also, it has to be easy to recover, even in the worst case scenario. Because of how Longhorn was designed, it's really hard to lose your data. Even if you don't have any Longhorn system or Kubernetes system running, as long as you still have a replica which contains your data on disk, you can still extract from that. And the Longhorn is designed with non-disruption upgrade, which means like you can always easy to keep it up to date and without worrying much about I have to schedule downtime for this to really interrupt my production workload. So let's talk about the architecture on the engine level. Here I have two nodes, and each node with such enough SSDs, RAM, and CPUs. And when the Kubernetes create a pod, it requires the volume, and the Longhorn see that request. We'll create two replicas on two different nodes, and we're going to create engine and to connect it to those replicas and provide this engine and to the volume. So the engine will in fact expose a block device, which the Kubernetes can bind mounted locally and provide as the volume requested to the pod. What if we have more pods requesting more volumes? We'll do the same, and we'll do the same. So there are two things in this diagram, right? The first thing is you can see each of the data paths of each volume. It's not really intertwined together, and each volume has its own engine and has its own replica. If the replica, like one replica goes down, or you have some issues with one volume, that has been in the traffic wide, it has been separated from the other volumes. The data path, in fact, is very independent among all the volumes here. And the second thing is, you can see the engine and the volume are always on the same node. That is by design. Because the major HA event with like the node failure event is the major thing we want to prevent. And we, of course, when the node failed, we want this workload to be migrated and the data stay intact, right? So the engine is not designed to be highly available by itself. It's designed to be co-located with the pod, and whenever the node goes down, the engine will be, of course, goes down with the pod. So Kubernetes and Longhorn can easily restart it from somewhere else, right? So that's greatly reduced the logic of the engine to try to make it more highly available. But now you have to hold these moving pieces, right? So how are you going to like really deploy it in the different nodes among like a cluster of tens of hundreds of nodes? That is where Kubernetes come in. We utilize Kubernetes to orchestrate all this deployment on the data level. So let's talk about a little bit more in the detail. You can see that for each node, if they have disk, used for Longhorn, and they will have engine instance manager and the replica instance manager. So this architecture is getting changed, but I'm talking about like in the 1.5, and we are merging the two together. This is what the architecture looks like in the 1.4 or before. So of course, Kubernetes requires the volume, and the replica created, engine created, and the volume was provided. Same with the pod B, and same with pod C. Now, what if the node A is down? You can see that the connection to anything on the node A will be cut. For example, pod B and pod C's volume, they used to have like 2 replicas, but now they only have 1. So this switch is on the millisecond level. As soon as Longhorn detects something is down with 1 connection, and from the Longhorn side will cut that connection and redirect the traffic to all the remaining replicas. So that's what's happened with pod B and C. But like this is Kubernetes, right? So we are like on the Longhorn side, in fact, we are helping Kubernetes to fencing node 1, and Kubernetes then will decide to bring the pod A back on the node 3, even though 3 has no storage. And when that decision was happening, Longhorn take that request and start an engine. Engine is stateless. It doesn't have any state in there, and the state all in the replicas. And that engine we're going to connect back to the replica on node 2 and provide that storage back to the pod A, so your workload will continue to run. So that is how the failure works, like how the failure was handled on the data level. So on the architecture side, and we look at a little bit more high level on the manager or control plane. And this is how we interact with Kubernetes. So Kubernetes clusters, whenever they have a request coming to, say, request a volume, and they will talk to the Longhorn CSI plugins through the CSI interface, which is stand for Container Storage Interface. So Longhorn CSI plugin talk to the Longhorn manager versus API, and the Longhorn manager is using Kubernetes API server to store all the metadata and orchestrate all the volumes. Longhorn manager saw that request, start the engine and replica on corresponding nodes, and start providing the data to the pods. And more requests, more engine, more replicas, and so on. So we also have a Longhorn UI, as I mentioned before, to talk with Longhorn Manager versus Longhorn API. So the Longhorn UI, in fact, serves as a complementary function to the CSI interface. The CSI interface only defined the basic level of volume management, like create, delete, and sometimes resizing, attach, detach, those kind of stuff. But Longhorn UI provides you the full functionality of the Longhorn system, which including node management and the backup restore, snapshot, everything, right? So all this extra function before they made into like CSI interface can be accessed by the Longhorn UI. Okay, let's talk about the feature and the future roadmaps on the Longhorn side. So I mentioned previously, there are a lot of Longhorn users are in fact using Longhorn for the cloud environment. And why is that? Well, first, I mentioned there's limitation on how many devices, storage devices you can attach to a single node. But also, there's a few specific enhancements we added in the Longhorn to support the cloud providers better. A common case here is if you're running, for example, on AWS, and you know there's a concept of the region and zone. And then you also know EBS volume are in fact tied to a zone. Like physically it's tied to a rack in that zone, but it's tied to a zone. So it cannot be migrated or accessed by any other workload on another zone, even they are in the same region, right? So in this case, pod 1 has access to the data through the EBS volume directly, and the pod 1 is like zone 1A is somehow down, right? So your data will be stuck with EBS volume on there. And even you start another pod on the zone 1B with node 2, there's no connection. You have to wait until the zone 1A comes back to continue your workload. But if you have Longhorn in the picture, the same scenarios, of course, this is going to add up the cost, which means like your EBS volume will need to have like more space on each zone, and there's computing and network cost associated with that. But in exchange, you have more highly available system, more robust system in place. So if you have, like in this scenario, pod in the node 1 is talking to the Longhorn engine who talk to the Longhorn replicas spread across the whole region on the zone 1A, 1B, and 1C. So if the zone 1A goes down now, Kubernetes can still restart this pod on the node 2, which is in the zone 1B, and that can, like, we can restart the Longhorn engine and connect it to the remaining replicas and make sure that your data like still accessible by your workload. Ironically, EKS is in fact deployed across zone by default to provide your high availability. But this limitation on the EBS is a problem our customer facing, and they are using because EBS cannot be accessed across zones, right? So this is the one typical use case why our users are using Longhorn to achieve the higher availability on the EKS side. Another use case is in fact related to a more advanced feature of Longhorn. So as I mentioned before, Longhorn has a backup mechanism built in, and you can back up Longhorn's like whatever, all your data, all your volumes into S3 or NFS backup store. I would normally recommend S3 over the NFS though. So, and that backup is incremental, and they will like continuously getting the update based on the interval you're setting, like once a week, once a day, and you can have multiple scheduling there, no problem. But in fact, Longhorn also provide a disaster recovery feature, which can preemptively like download the data from S3 into another region, which you can have a volume standby there. So this mechanism is also incremental. Longhorn will detect what has changed in the upstream S3 backup store or NFS backup store, and then restore the changed part into the volume that's in standby mode in the new region. So if the class A, like the region A, goes down, and you will have you can react it by easily flip up and set the region B's volume to active state, and then stop your workload on the region B. So that's greatly reduced your downtime for your main workloads. Of course, this only going to take care of your data pad, and for this to work, you also need to work on your DNS, your network, load balancer, all these things together. But Longhorn provide a solution just in the great schema of having a cross-region failover here. All right, so I'm going to talk about the roadmap soon, and before that, I was asked to put this safe harbor statement in. The purpose is whatever I'm talking here is in fact subject to change, and especially all the timelines, feature list here is no obligation, and so on, right? But let's dive into it. So this month we are going to release Longhorn 1.5, and on the volume side, I do have a much fuller list of the features, but those are the major ones. We already have stream provisioning, snapshot with schedule, and you can do backup schedule and restore with schedule, as I mentioned before. You can do volume expansion. You can do volume clone. We also provide end-to-end encryption, and that is, I think, added last year. And cross-AZ scheduling, that is what I mentioned before on the AWS case. And we also have added the bit rodent detection. So for your nodes or for your VMs, they normally have they very common to have different speed and different IOPS for different like underlying disk. And Longhorn allow you to select different nodes and different disks by using the storage tag feature we have. And that's like some of the code data you might want to put into the spinning disk, some of the hard, like more primary use the data, you want to put that in SSD or VME, right? So we also support cross-cluster disaster recovery volume with defined RTO and RPO. That's what I mentioned in the last slide. And life upgrade, sure. Remaining support and ARM64 are both G8 right now. And we have supported extra CSI protocol for the snapshotter. And Longhorn has added premises support to provide metrics to the premises and to collect and see how the storage layer is doing. We have added data locality support, and that is more for the use case that many applications might only want to, they have like replication or sharding mechanism by themselves, and they only want to access the local disk for that, and they want to have like a better performance. So that's there. And we support automatic recovery Kubernetes management workload, and that is the way for us to complementary the failure detection and the failure recovery scenario for Kubernetes, like fencing the node and stuff. And we have intuitive UI and one-click iteration for sure. The biggest highlight here for the 1.5, in fact, the team has been working hard on it for quite a while, is the Longhorn engine based on SPDK. The Longhorn engine v2 is going to be released with the 1.5 release in the preview state. That means you shouldn't use that in any production environment or even near production environment. This is strictly like maybe in the lab and the POC usage, and this is not mature as our current engine is. But I do want to let you know, let you have a see to the future, what the future of the Longhorn looks like. So the Longhorn engine v2 is created based on the storage performance development kits created by Intel, and is our next generation of the data engine. So I briefly mentioned now, like Longhorn is using iSCSI protocol for exposing the block device, and Longhorn in fact has its own like private protocol for data transfer on some of the data paths. But starting on the Longhorn Engine v2, we're going to utilize NVMe over Fabric or NVMe over TCP protocol for whole stack. This is of course, the latest industry standard is optimized for the NVMe for sure, but we are using it as a standard protocol for the data plane communication in the Longhorn. And they were currently, as you know, Longhorn is using the file system and using some feature of the file system to implement the snapshot and other mechanism. And that will be the history, because starting with Longhorn Engine v2, and we have the ability now to use the entire disk or partition as you want, instead of working on top of the file system, and depends on the file system to do the sparse detection or some other work. Because many times, even we have certain direct flag and flush the data, there's some certain caveat we need to overcome with file system. That's why currently we only support on x84 and XFS. But using the whole disk and the partition will eliminate all that restrictions, and everything will be in our control. And the most exciting about the Longhorn Engine v2 is now we can provide near native performance with NVMe disk in the local volume pass-through mode. So our measurement, our benchmark will be public after 1.5 release. But I can tell you right now is if you are going to through the local volume pass-through mode, the latency we're adding on top of the native NVMe disk performance is less than 30 microseconds. So if you're measuring it, like say in terms of the, like currently, Longhorn performs extremely well in terms of the bandwidth, but on the latency and IO ops is still quite a gap compared to the native performance because the overhead we're adding on top, right? So with the NVMe's help and the new technology like pooling, I don't think that's new technology, but a different way of using with the right object, which is NVMe. So we are only adding about 30 microseconds, means like we're having the near native performance for if you're running on the NVMe or SSD. Of course, if you have the replicated model, the network latency will be factored in, but it is still going to be like I would say it's going to be one of the fastest storage system like in the industry right now. Right. It's still going to take time. We still need to invest more into it to make it more mature. So that's why the GA version is targeting probably a year from now. But now we have the first step out, and you can download 1.5 once it's coming out and give it a try and tell us what you think. So another exciting topic down the line on the Longhorn side is the object store. So this has been asked, in fact, a lot of times from the users, like you're supporting block and now you have the file system. When are you going to bring the object store support? So in fact, we are working on it. And you might know, like SUSE has internal project called S3 Gateway, and which is derived from the Ceph Rados Gateway project. And we want to make it more generic. And S3 Gateway will be the engine powering Longhorn object store support. So when it's down, you will have a Longhorn volume, like creating a different gateway for the client, and you are able to use your S3 client to access those S3 gateway endpoint directly and create multiple buckets and doing manipulation and doing user management all through the Longhorn interface. So the first experimental version of this object store support is targeting by the end of the year Longhorn release. So future releases. 1.6 we're targeting by the end of the year, and we will promote the Longhorn Engine V2 from preview release to the experimental, and they should have the feature parity to the Engine V1 at the time. And also we'll add experimental object store support in the 1.6 as well. And the local volume pass-through with SPDK should be GA'd by the time. And also we are introducing the concept of the volume group in the 1.6, and that's going to help you to back up and manage your group of like applications that's designed in a distributed way. So you can take a snapshot and backup like at a certain point, which like the data is stable. So Longhorn 1.7, and they will be scheduled on the Q2 2024. And SPDK data engine like Longhorn Engine V2 will be GA by then, and object store support will be GA, and that's including the zero downtime upgrade and HA deployment. And on 1.7, the most exciting thing we are going to support is the replica sharding, and this is to overcome the limitation of the disk size for each Longhorn replica. So that's very exciting for me to see the Longhorn has come so much into today, and with SPDK, with Object Store, with the sharding down the road, I'm really excited to see like the more user using it and love it and give us feedback about it. All right, so that's all on my presentation. And any questions?